This is just a couple of derivative topics you need to know how to do. The first is they may ask you to find where a specific slope occurs. So if you remember, a derivative is a function that can tell you the slope of something else anywhere. So at any point you can find the slope. So we may want to know where a specific slope takes place. Because when we start applying these things like speed, then the derivative really tells you the speed of something, and you may want to know where a certain speed occurs. So this says find the value of x where y equals 4x cubed plus 3 has a slope of 1. So we want to know where 4x cubed plus 3 has a slope of 1. Well, you remember that derivatives find slope. So when the slope is 1, the derivative will also be 1. So we're going to take the derivative of y equals 4x cubed plus 1 and get 12x squared. And we want that derivative to be equal to 1, because if the derivative is 1, then the slope is 1. So now I just find the value of x, so I solve for x. Divide by 12, I get x squared equals 1 over 12. Then take the square root of both sides, and I get x equals plus or minus the square root of 1 over 12. So there's two places that it will occur in this case, the positive square root of 1 over 12 and the negative square root of 1 over 12. Okay, now let's just look at the red one. It says find any places where f of x equals 1/3 x cubed plus 2x squared minus 1 has horizontal tangent lines. Okay, so we got to think here. If we have a horizontal tangent line, then that would mean that the slope would be 0, because horizontal lines always have a slope of 0. And if the slope is 0, that would mean our derivative is also 0. So we simply take the derivative, and we get x squared, 3 times 1/3 is 1, 3 minus 1 is 2, plus 4x, and then the 1 just goes away. So that's our derivative. And we want to know where it's 0, because if it's 0, the slope is 0, which would match up with a horizontal line. Okay, to solve this one, we need a factor, so we can pull an x out front and leave us with x times x plus 4. So the two numbers that will make this 0 are 0 and negative 4. So again, in this case, there are two places where horizontal tangent lines would occur. Now just so you know, these questions, I know my two examples, they were exactly two answers. That's not always the case. There may be none where these occur. There may be 1, 2, 3, or however many more it could be. The second thing you need to know how to do is higher order derivatives. Everything we've done up to this point is first derivatives. You also need to know how to do second derivatives. Here's the notation. You have the original function, the first derivative, the second derivative, and third derivative, and so on. And you see how it's written for both Newton notation, which is on top, the f of x, the f prime, and so on, and Leibniz notation, the y, the dy over dx, and so on. But it's very simple. If they ask for the second derivative, like our first example does, that just means take the derivative twice, or take the derivative of the derivative. So we have to find the first derivative first, and we get 16x cubed minus 6x. And then we take the derivative of that, and we get 48x squared minus 6. So that's the second derivative. So it's really not complicated. It's just doing the same thing more than one time. Our last example, we have, answers are up here. Don't look. We have the second derivative. Notice they started by giving us the second derivative. 4x to the fifth minus 3x cubed plus 4 is the second derivative, and they're asking us to go all the way to the fifth derivative. Well, make sure, though, you pay attention to the fact you're starting with the second derivative, because that way you're not going to do more than you need to. So if we're starting with the second derivative, the next one down would be the third derivative. That'll be 20x to the fourth minus 9x squared. Then we take the derivative again and get 80x cubed minus 18x. That's the fourth derivative. Then we take the derivative of that, finally 240x squared minus 18, and we get the fifth derivative.